Hello dear students, welcome you all for transmission and distribution class. So continue with the line constants. Today we will see the flux linkages. In the previous class we have seen the resistance. Today we will go to see the inductance. So inductances we are knowing that inductance is L is equal to xi by I, where xi is nothing but the flux linkages. As studied earlier, the inductance of a circuit is defined by the flux linkages per unit current. Therefore, in order to find the inductance of a circuit, the determination of flux linkage is the primary importance. So we will discuss the two important cases of the flux linkages. So the first one is the flux linkages due to single current carrying conductor, and next is flux linkages in parallel current carrying conductor. So first we will see the flux linkages in single current carrying conductor. So consider a long straight cylindrical conductor with radius r meters and carrying a current of I amperes, RMS value. Shown in this figure 9.4, you can see the figure. One cylindrical conductor is carrying a current I with its radius r. Okay, the current is set up a magnetic field, and the magnetic line forces will exist inside the conductor as well as outside the conductor. Both of this flux will contribute to the inductance of the conductor. Means when a conductor is carrying a current, it produces its magnetic flux. Both inside the conductor as well as outside the conductor, the flux is set up. That flux is due to the current I. The total fluxes inside the conductor as well as outside the conductor is going to set up the inductance. So we will see. First one is what? Flux linkage is due to the internal flux. Internal flux means the flux which is inside the conductor. So we will see the figure 9.42 where the cross section of the conductor is shown. The magnetic field intensity at any point x meters from the center is given by. You can see these things clearly. Here a cross section is taken with r as a radius, and in between a small area is taken dx, and which is having a distance of x from the center. Okay, the magnetic field intensity is given by hx. X is suffix is given for the distance at x it is there any point in the conductor. So hx is given by ix by 2 phi x, which is magnetic field intensity is current per area. Okay, so assuming uniform current density is there, we can tell Ix is equal to phi x square by phi r square into I, because from anywhere from the center to the till periphery of the conductor, everywhere current density is same. That's why this equation is shown, which is nothing but x square by r square into I will give, means if x is same as r, means the radius is same as the x, or from the center the distance you are taken as radius only, then r get cancelled. Current I is same as I, that is the condition here. So hx is given by x square by r square into I into 1 by 2 phi x, or it is nothing but x by 2 phi r square I ampere turns per meter. If mu is the permeability of the conductor, then flux density at the considered point is given by, we are knowing what is the relationship between flux density and magnetic intensity, flux intensity, that is B mu H, or for here Hx is considered, so I will take flux density as Bx. Bx is equal to mu naught into mu r into Hx, Webers per meter square, where mu naught is the absolute permeability and mu r is the relative permeability of depending upon the magnetic material. Mu r is 1 for the non-magnetic material such as air and all. Okay, so we will write here Bx is equal to mu naught mu r by Hx is nothing but x by 2 phi r square into I, or for if non-magnetic material is used, then mu naught is only to be taken, mu naught xi divided by 2 phi r square, Webers per meter square. Now flux d phi through cylindrical shell of radius thickness dx and axial length 1 meter is given by the flux d phi is equal to flux density into 1 into dx, or mu naught xi by 2 phi r square into dx Weber. This flux links with the current Ix, which is nothing but I phi x square by phi r square. Therefore, the flux linkage per meter length of the conductor is given by d psi is equal to phi x square by phi r square into d phi, or which is finally written as mu naught Ix cube by 2 phi r raised to 4 dx Webers per turns, Webers turns. Total flux linkage from the center up to the conductor surface, that is flux linkages in internal, is given by, this is xi is for only for the particular area. Now inside total conductor we can take it as psi internal is integration from 0 to r mu naught I x cube by 2 pi r4 dx, or after integrating and putting the values of x as 0 and r, higher limit r and lower limit 0, we will get mu naught I by 85 Webers per meter length. So here it is very clear that the flux density is measured, flux linkages is measured with the current only. If current is more, flux linkages are more. If current is less, flux linkages are less, and it is internal flux is not depend upon the any conductor size or cross section. It is purely dependent upon the current. So now the same single conductor with the external flux, if now inside the conductor is over, due to the same current external flux is there. So that is we will see using this figure 9.5, where we will say take one small area which is having a distance of x meters from the center, which is outside the conductor. Okay, so that same hx is given by I by 2 pi x ampere turns per meter. Same flux density bx is given by mu naught hx, which is mu naught by I 2 pi x, which is we are seeing. Now d phi is through the cylindrical shell of thickness dx, and axial length 1 meter is given by d phi is equal to bx dx. That is flux is nothing but flux density into the small area df. So we will get mu naught I by 2 pi x into dx Webers. The d phi links with the current in the conductor once and only once. So the d psi is nothing but d phi, that is mu naught I by 2 pi x dx Webers turns. Now this is the small area, small flux. Now total flux is taken by the integration. Where to be integration to be done? In the previous case, starting from the 0 point to the r, that is internal flux. External flux starts from the outside surface of the conductor, that is r, till infinity. So the integration is done from r to infinity. After integrating that one, we will get that xi external. The external flux of the conductor is given by integration r to infinity mu naught I by 2 pi x dx Webers turns, or overall flux linkages phi is given by phi internal plus phi external. We will add both the internal and external fluxes, and finally we will have a small simplification that psi is equal to mu naught I by 2 pi as common into 1 over 5 plus integration of r to infinity dx by x. So this is regarding the flux linkages due to the external fluxes. So this is what the one conductor, that is flux linkages due to a single current carrying conductor, single carry. If it is having number of conductors, then each conductor's internal plus the conductors with other conductors also need to be taken. That we will see in the next class. For the time being, you try to understand this concept first clearly. You go through this one and you derive by your own to get the flux linkage equation, when flux linkage is due to single current carrying